Hello, this is Vincent Kennedy, and this is my submission for Project 2, Couette and Poiseuille flow combination. And let's just get started. We're going to start the project by getting fluid flow fluent, and changing our geometry to 2D. Then going into new design modeler geometry. Okay, then you click the Z axis, go into the XY plane, and start sketching. First, we'll change the units to millimeters, and then click rectangle and create a rectangle. Then we need to go into dimensions and make these 2 dimensions. These are dimensions based on the requirements of the assignment for the length to be 150 times the height and for the Reynolds number not to be above 2,500. So I chose 3 millimeters height and 450 millimeter length. I got this from previous examples in this class, so it should be working fine. The Reynolds number calculated was way below, was far below the required Reynolds critical. So we'll start with creating a concept, surfaces from sketches. I go into the XY plane, sketch, apply that. There we go. And we hit generate. And that should create a nice surface here. It does. That means we could continue to the next step, setting up the mesh. So we update geometry, go into mesh, start it up. This program usually takes the longest to start up, so just gotta wait here for a little bit. All right, here it is. So we're gonna start our mesh with insert, method, automatic method. Click this, and click apply. And this will set up our quadrilateral dominant method. Next, we go into mesh, insert, and sizing. For this, we're going to select 2 edges, the start and the end. Did that select both? It did. All right, that should work. Let's just zoom in. Yes. So next, we're going to change this from element size to number of divisions, and click 60 for this one. Then we're going to change capture temperature to no, and set soft to hard. That'll complete our changes to this sizing element. We're going to create one more sizing element. Instead of side to side, we'll do top to bottom. Apply. Element size to number of divisions. 750 divisions. Set capture curvature to no, and from soft to hard. That should complete this sizing element. Let me just get a quick check on the numbers. It is correct. And so we need one more. This one would be a face mesh, where all we need to do is select the face and click apply. That will do everything we need to do for this one. Nothing further is needed. Then we hit generate. And we know it should be correct if this mesh looks completely black and all these units look fairly uniform and rectangular. So that's correct. The start and end should also be like that if we were to zoom in. If I could do that, but I'm fairly certain this is correct. So we're going to move back into the workbench, refresh our mesh. Actually, we still need one more thing to do in the mesh. We need to name our edges. This is very important for the setup stage. Click that, click N, and then this would be upper wall. Upper wall. This one down here would be lower wall. This over here would be inlet. And over here on this side would be outlet. Looking at the name sections, upper wall, lower wall, inlet, and outlet, it seems we have everything we need. Now we can go back into the workbench. Refresh our mesh. The green check mark means we can now move on to setup. We're going to do double precision and solver processes 2 for this one for me. That's my preference. Click start. This one also takes a fairly long time to start up. It'll finish loading in just a sec. Alright. Seems to be working itself out. We still need to wait for the object to show up. There it is. We got the correct inlet and outlet and solved that for us. Now we need to change a couple of things. Models, we need to change our viscousness to laminar. So this, get rid of all of that extra stuff. Really click OK. Then we need to check in on our materials, our fluid, and its air. This was built in with air in mind so that the Reynolds number is below that 2,500 mark for the critical number. So let's check on it, make sure the values are all okay. It does seem to be the base default air. So we'll just close and minimize that. Our next step would be to start up our boundary conditions. Inlet is our first thing to be set up. We had a free-flowing velocity of 5 meters per second. So we just input that, click apply, make sure that it hits apply, close. I'm going to open that one more time because I've had some errors in that previously. Still looks good. Close that. I'm going to work on our wall velocities. The lower wall we'll do first because this is a little weird. We're going to hit moving wall. Our speed was 2 and our direction was in the negative x direction. Hit apply, then close. Then we can work on the upper wall. Click moving wall again. This time the speed was 3 and the direction was in the positive x direction, so that can stay. And we can just hit apply. And click close. Then we can close this section as well. So our next section that we need to mess with would be the initialization. We hit initialize. That'll initialize our process. This will show us it's done. Then we can move on to running calculations. So I'm going to choose, I think 200 was the one that I was shown in previous examples. This is based on a preference on accuracy, but 200 seemed to be a good number when I did it. So this might take a little while. These will all trickle down. Get our calculation complete. Now we can start working on our graphics and other such things. So we're going to work in this section for a little bit. So we're going to get part A done for this thing, for this project. Getting the velocity contours and vectors in the same plot. So we're going to open up contours, change this to velocity, select all our surfaces, and save and display. That one more time just to make sure. This all looks good. Let's zoom in. We got our developing region right there. Everything looks good. And yep, seems to be already developed all the way through. We'll see that result later. So we click close, and then we can go into vectors. We need to make a velocity vector. We need to seed on all of these, and we'll hit save and display as well. This will show our velocity vectors, which looks really good. Our bottom is flowing backwards because the wall is moving backwards, and the top is flowing to the right. The middle is also flowing to the right. So, save and display that one more time, and hit close. Next, we'll hit scene. This is where we'll combine our contours and vectors. So transparency is up to you, but I saw that around 80 worked pretty good, so I'll just hit around 80. Then I'll hit save and save and display. I don't think I see the contours, so it doesn't look like it worked. Give me just a sec. Get down to about 40. How about that? It still seems a bit out of place. Let's set this down to about 30. Oh, it's there. It's just a little too transparent. I don't know why I'm getting different results in this film, but the visuals are there. It just seems to be in a weird overlay, it would seem. But we get our contours and our vectors, so it is right here. So we can hit cancel, and we can start working on another section of this. So we can start working on our pressure contours. This is fairly simple. We just go back into graphics, contours, and pressure. We're already there. Select all our surfaces and hit save and display. Interesting. Not realize why my system is doing this, but I'll just zoom out. Zoom in. It looks far better zoomed out than it does zoomed in. It seems like it's a banded color scheme, but it's not what I selected. So we'll just stick with this, but it should be working. So yep, this is our static pressure. We can do the same for dynamic pressure. We can zoom in and see all those values. Gets fast in the middle, slower in the bottom and the top. And we can also do the same for, we can also see our developing region if you would like to see that. Right here is our nice developing region. You can see that it is getting faster towards the center and developing from uniform to less uniform. So then we can go into our total pressure. Save and display. We also get that developing region effect. We can look across. We can see these values and how it changes from the beginning to the end. Okay. And then we can close. That should be it for the pressure contours. And we can move on to creating our velocity profiles at the midsection and end sections of our pipe here. This one's a little bit more complicated, so let me pull up my previous instructions on the other side. You can't see that, but let us go into XY plots. Here we are, XY plots. For this, we're going to need a couple extra surfaces. Line rake, we're going to need two. We're going to need a midpoint and a endpoint. If you remember correctly, our X values should be the middle for this 450 millimeter long, and so it should be 0.225, if I am remembering correctly. Yes, 0.225, and our Y value should be from 0 to 0.003. Should be our height. So it should be 0.225 meters deep and that high. We can create that, and then we can create our endpoint. So this is also a line. It should also be 0.003 from 0 to 0.03 for our height. But instead of this value, we're going to need 0.45. So you could use 0.45, but I like to use something a little smaller because the results will be a lot more accurate, since the velocity tends to get a little bit messed up at the very end due to the exit. So we can create that, and we can close this. So then we can create a velocity. We need the direction vector, and then we need the velocity and the velocity magnitude, and then we can create all of this and save and plot. Oh, we did not need all of those. That's my bad. We only needed midpoint and endpoint. Oops, I did it again. So save and plot. Did that do it? Should have. Interesting. I believe this should be switched around. There we go. So we have this graph right here. And it does seem to have a little bit of trouble with this, but these lines should be overlapping, which is why you can only see one. Yes, as we can see, they're very close together. This should be our velocity profile. Right here. I do not understand why this is not working like such, but it is enough proof as example. It should increase and then decrease into the negatives, -2 range. So we can close this, and we could start looking for our maximum velocity and height. So to do this, we can go into reports, surface integrals, and we could look for, let me look for it. It would be vertex maximum, and we can go to velocity magnitude, and I believe if we can just click all of these, and it'll show us our maximums for all of them. And so we can see that we end up with a maximum velocity of 7.436757. That would be our maximum velocity in the cross section. And then if you wanted to find the y value for that, you would just look at this graph, find where it reached its maximum. That would be at this point right here. And we can see that it found its maximum at 7.43 meters per second and 1.75 millimeters tall in the pipe. So that's what you would put in for your maximum velocity and its location in the pipe. So the next step would be to determine the pressure gradient using the fluent results with theory. This is not done in ANSYS and Fluidan. It is done on our piece of paper. I do not have that for this video, but if you want to take a look, it is in my submission in a PDF form and handwritten. So thank you for watching this and grading this, and have a good day.